This video is all about the inverse hyperbolic functions. So we've seen in the previous video that sinh, cosh and tanh are our new hyperbolic functions. And just as the same way as we have inverse trigonometric functions, we also have inverse hyperbolic functions. The inverse of sinh is r-sinh, the inverse of cosh is r-cosh, the inverse of tanh is r-tanh. Notice that we have some domain restrictions here that I'm going to talk about as we look at the graphs. Excuse me. Okay, so remember how we find the graph of an inverse function. It's the reflection in the line y equals x. So if I take my sinh graph here and reflect that in the line y equals x, I get the graph of r-sinh. Notice that because sinh was a one-to-one function, there is no domain restriction required here at all. There's also no restriction on the range. But with cosh, remember that the cosh graph, when we did this last video, was actually like that. But that's not a one-to-one function. Therefore, its inverse, r-cosh, would not exist. So to overcome that, we restrict the domain, and we say that x has to be greater than or equal to 0. So that now means that cosh is a one-to-one function. This is now a one-to-one function, which means that its inverse will exist. So I can now reflect that in the line y equals x to get r-cosh. Also note, the range of cosh was that y is greater than or equal to 1. And remember how the range and the domain switch for an inverse function. So if the range of cosh was y is greater than or equal to 1, then the domain of r-cosh is that x is greater than or equal to 1. In a similar way, remember the domain of cosh was x is greater than or equal to 0. So therefore the range of r-cosh is that y is greater than or equal to 0. The only of one was tanh. Notice here that tanh, the domain of r-tanh is that x is, the modulus of x is less than 1. That's the same thing as saying that x has to be less than 1 but greater than minus 1, which should make sense because remember that the tanh graph had a range between 1 and minus 1. So it should make sense that the domain restriction of r-tanh is that x has to be between minus 1 and 1. So those are the inverse hyperbolic functions. Now we've seen that the hyperbolic functions can also be defined in terms of exponentials. We've seen that sinh can be defined as e to the x minus e to the minus x divided by 2. And so it would make sense then that the inverse hyperbolic functions could be defined in terms of logarithms. And they can. This is how they are defined. These are formulae that are provided to you in the formula booklet, but you could be asked to prove them as well. So that's what I'm going to do now. We're going to prove that r-sinh x is defined in terms of logarithms as ln x plus square root of x squared plus 1. So let's start off with that one. So first thing I'm going to do is I'm going to say let y equal r-sinh of x, and then I'm going to take sinh of both sides. So sinh y is equal to sinh r-sinh, which cancel out just to be x. That will allow me to use the exponential definition of sinh as e to the y minus e to the minus y over 2 equals x. I'm now going to multiply both sides by 2. And then this here, I can think of that as being 1 over e to the y. So I'm going to multiply through by e to the y. E to the y times e to the y is e to the 2y. 1 over e to the y times e to the y is 1. And then I've got 2x times e to the y. I'm going to move everything over to the left-hand side to make this equal to 0. Like that. Now, here comes a slightly tricky bit. I'm just going to create a bit more space for myself. And bear with me. Because what I want to do here is complete the square. I'm trying to get y as the subject here. That's what I'm trying to do, because remember y is equal to r sinh. So I'm trying to rearrange this to make y the subject. Oh. Yeah, that's better. So this is like a quadratic, with this being the x squared term here and this being the x term here. So I'm just thinking of this as being the coefficient in terms of me completing the square. So remember that when we complete the square, I halve the coefficient. So this will just be a 2. So that'll just be an x now. I'm halving the 2x. I'm then going to take away the x squared, and I've still got the minus 1 on the end there. Just to make it clear that that is the same thing, if I were to expand this out, I'd have e to the y times e to the y is e to the 2y. I'd have e to the y times minus x, but I'd have 2 of those. I've then got the minus x all squared, which would be plus x squared. Then I've got the minus x squared minus 1. So hopefully you can see that this is the same thing as this, in completed the square form. Right, remember I'm trying to get y as the subject, so the next thing I'm going to do is move these x squared plus 1s to the other side. And I'm going to square root. Remember that when I square root, it will be a plus or a minus. I'm then going to add x to both sides. So I get e to the y equals x plus or minus root of x squared plus 1. Now, I can ignore the minus here. The reason why I can do that is because x squared plus 1, all square rooted, that's always going to be bigger than x. Therefore, x minus something that's bigger than x will be negative. And e to the power y can't be negative. Let me just repeat that one more time. This term here is bigger than x. The reason why I know that is because of that plus 1. If it was just x squared like that, then that would obviously be equal to x. But the fact that I add 1 before square rooting, that means it has to be bigger than x. And so, because this is bigger than x, if I did x subtract that, it would be negative. Therefore, I can ignore that negative. I can delete that. And now I can take logarithms of both sides to get y equals ln of x plus the square root of x squared plus 1. And remember that y was originally defined as my r sinh x. And we're done, we're proved. We've shown that r sinh x is ln of x plus the square root of x squared plus 1. Next, let's do the r cosh. We're going to follow the similar procedure. It is quite a long, complicated procedure, so I think it is worthwhile us doing a second example. And there is another thing to bear in mind at the end as well. So we want to show that r cosh x is equal to ln of x plus the square root of x squared minus 1. And remember that for r cosh, x always has to be greater than or equal to 1. Remember that is the case because the range of r cosh, was always greater than 1. Therefore, the domain of r cosh is always greater than or equal to 1. Right, so let's follow the same procedure as before. I'm going to set let y equals r cosh x. So take cosh of both sides to get cosh y equals x. And now use the definition of cosh in terms of exponentials. Times both sides by 2. Reimagine this e to the minus y as being 1 over e to the y. Multiply through by e to the y to get e to the 2y plus 1 equals 2x e to the y. Make it equal to 0. Like that. Next comes the completing the square stage. So again, like I did before, I'm just going to rub this out to create some more room. Again, just bear with me. Right. So completing the square. We've got our e to the y at the front. I'm halving my coefficient there, so I'm halving the 2x to get x, all squared. Take away the x squared, plus 1 equals 0. Right, same idea as before. Move the x squared and the minus 1 to the other side. Square root. And then I'm going to add the x to both sides. Now, in the previous example, I could ignore the negative because because I knew that e to the power y had to be positive. But in this case here, I can't use the same logic to do that. It could, at the moment, be either of them. Because the x squared minus 1, when I square root that, because it's a minus 1 now, that's going to give me something that's less than x. Therefore, when I do x take away that, so let me just repeat, this is going to be something that's less than x, because if it was the square root of x, then that would be equal to x. Sorry, if it was the square root of x squared, that would be equal to x. So me doing that will make it a tiny bit less than x. So therefore, when I do x take away something that's a little bit less than x, well, this is still going to be positive. So in both cases, this is positive. So e to the y is fine. I can now take logarithms of both sides. Like that. Again, this is still fine at this stage. Now I'm going to rewrite y. Remember, I said that y was equal to r cosh. Excuse me. Now, it's at this stage where there is now an issue. Let me just put what I've done there in a box, just to make it stand out, and we can compare this to what I was asked to prove. So I was asked to prove this. Notice that I have got a minus where I shouldn't have, and it's not because of the same reason as before. The reason why this minus shouldn't be there is because r cosh is always positive. Remember the r cosh graph we saw earlier on was like this. It was always positive. And if I have this negative inside here, remember how I was saying that then I would have ln of x minus something that's a little bit less than x. Well, if x is greater than 1, then that is always going to be less than 1. If x is greater than 1, then x minus the square root of x squared minus 1 is going to be less than 1. Therefore, ln of a number that is less than 1, ln of a fraction, for example, is negative. ln of anything less than 1 is negative, which it can't be for r cosh. R cosh has to be positive. So that is the reason why I can ignore that negative. And final thing for this video. Just a couple, 3 examples of actually using those definitions to substitute some values in. So I want to express as natural logarithms, so in terms of ln, r sinh 1, r cosh 2, and r tan 1/3. So r sinh 1, let's use the definition of r sinh for this. So that's going to be equal to ln, remember it's ln x, so ln 1 plus the square root of 1 squared plus 1. So that's going to be ln of 1 plus the square root of 2. And that's it. That's r sinh of 1 expressed as a natural logarithm. Let's do r cosh now. So r cosh of 2 would be equal to ln of 2 plus the square root of 2 squared minus 1. which is equal to ln of 2 plus root 3. So that is r cosh 2 in terms of natural logarithms. And then finally, r tanh of 1/3. R tanh is a half ln of 1 plus x, so 1 plus 1/3, over 1 minus x, so 1 minus 1/3, which will be a half ln 4/3 over 2/3, which simplifies to be ln 2. So a half ln 2, or if you wished, you could do it ln of root 2. And there we go.